Hi, my name is Helei Duan. I'll be presenting our work on learning task space actions for bipedal locomotion. Legged animals spend a long time learning and refining motor skills in order to achieve agile motions in many unstructured environments. When we look at how infants learn to walk, it seems all happen naturally. But we would like to ask what is important for learning in the first place before even learning to perform athletic movements. At first, baby explores how to move their feet while being supported and are still not capable of walking. Later on, they figure out how to properly place their feet when standing up and learn to walk. In this study, we're interested in the following question. What are the natural actions that can gradually lead to learning locomotion skills when animals move around with legs? We aim to understand leg locomotion from a bottom-up approach and let our robots learn to walk first and eventually show great agile and dynamic motions via reinforcement learning. The learning process may have to reason about robots' own dynamics when applying torques and making frequent contacts with the ground. Our goal is to understand these low-level interactions with the environment first, even before building more abstract cognitive and intelligent models. For example, the video shows our robot Cassie attempting to step over challenging terrains. It is very interesting to think about what actions are most efficient to learn such locomotion skills. There are a couple options for Cassie to select and act. The first option is to learn by exploring with joint actions, such as torques or joint set points. However, it could be really hard to learn how to adjust each joint actuator under many locomotion scenarios. Another option is to explore with the action of the feet in task space. When our robot Cassie wants to overcome the gaps in front of it, the immediate actions could be where to move its feet and how to apply forces on the feet in order to build up enough momentum to achieve a successful step over the gap. In order to get more rewarding solutions for faster learning, animals tend to explore more in task space than in joint space, such as trying out all possible foot positions during leg swings, and care less about per-joint actions. For example, when we are walking around, we tend to pay less attention to a particular muscle. So we ask the question, what should be the control space for bipedal robots to learn locomotion skills? Many previous works show that learning to walk is possible with joint actions, but this approach comes with some drawbacks. First, learning and exploring with joint actions tend to require a lot of samples and time to train, especially for legged robots with a high-dimensional actuation space. Also, exploring using random noise on each joint is unstructured and uncoordinated, making it hard to find viable sequences of commands for the robots. We believe that an abstraction of action space is necessary towards learning for high-level reasoning. Instead of learning exactly how much joint movements to take, reasoning about the actions of the feet, whether in the air or on the ground, can greatly simplify the learning problem, while still capturing the key low-level interactions that are important for legged robots. Therefore, we propose learning control policies for bipedal robots in task space actions. When we train policies with reinforcement learning simulation, the agents ultimately need to control the actuators. For joint actions, the learned policies can directly control each joint. But for actions in task space, the robot doesn't know how to actually issue joint commands to move the feet. So we added our knowledge into the system with a model-based controller that transforms learned foot actions into torques. Here is an overview of our approach. We use the reinforcement learning to optimize reactive control policies that takes in state information and output actions in task space. The policy is running at 40 Hz shown in red, output the desired foot set point residuals, and the policy is represented with the feed-forward neural network. The states include desired body velocities, robot joint encoder values, robot body information, and feet positions. Additionally, the input states also include a phase variable that acts as a periodic clock to synchronize the foot in swing and stance during the gait cycle. The reward for the learning intends to track the body velocities, but not tracking any foot trajectories, and the clock defines whether each foot should be in a swing or stance. We use proximal policy gradient with actor critic networks to optimize the policy. Please see our paper for details on policy optimization and training algorithms. Once the policy sends out the learned set points residuals for both feet, then we use a task space controller that maps the learned actions into torques and run at 2 kHz. The controller design includes swing and stance control. Transitions between those is smoothed by the phase variable. Our trajectories are based on bipedal spring mass model. Please refer to our paper for more details in the controller design. We also implemented the same learning setup, but using joint actions as the policy output, so we can compare the difference on the learning efficiency. In the plot here, green line indicates how many samples spent during training. Blue curve is for task space actions, red curve is for joint space actions. Early in the training, both actions are struggling to coordinate and produce stable behaviors. Policies with task space actions are able to walk within 10 millionths of samples, approximately 8 hours of walk clock time, whereas joint space would spend 32 hours and more samples to get to the same reward level indicated by the star symbol. Both action spaces produce locomotion behaviors in the end. Our results show that learning is at least 4 times sample efficient when learning actions in task space than joint space. But why do actions in task space learn faster? We look into the training dynamics in details from early on to the final policy. Early on in the training, learning mostly applies stochastic noises on each action space. We see the differences in the resulting explorations in terms of the feet positions. Task space in blue shows much more spread out distribution, indicating the noises are more structured in terms of the joint coordination. On the other hand, the joint space, even applied with the larger noise values, does not have the same result. This might potentially explain why the low-dimensional actions in task space could lead to better chances of quickly exploring more rewarding solutions. When the policy is fully trained, we tested the policy in simulation with various speed changes for steady-state locomotion. Both action spaces show similar performance on the speed tracking in simulation, up to 1.5 meters per second. We also see some interesting differences in terms of the ground reaction forces during stance, which is a key aspect of researchers look at to quantitatively determine the low-level interactions. It happened that task space actions produce and match the force profiles really well with our reference signals as well as what we see among the legged animals. But in the reward, we actually do not ask for matching these forces. When in the joint actions, the policy does not match or produce the desired force profiles. This is a very interesting point that we will investigate in the future directions. We then demonstrate our sim-to-real results, where we deployed the learned policies on our robot Cassie. Policy and controller run at the same control rate as they are in simulation. Cassie is able to walk at various steady-state speed on the treadmill, with fairly quiet impact sounds when foot touches down. Here is a short clip of hardware demonstrations. And Cassie starts to slow down and start stepping place. In this work, we present our approach on low-level learning of steady-state locomotion for bipedal robots. We represent the agent's actions in terms of feet in task space. We also demonstrate successful sim-to-real transfer. These results encourage us to move towards learning more complex control policies using actions in task space. Future research may include: first, extending task space actions with centroidal dynamics. Second, it is worth looking at how to embed the notion of efficient exploration in task space into joint space approach. Because we do notice that directly giving joint coordination information to learning does help to learn faster, but it might prevent the discovery of interesting joint couplings. Third, it will be very interesting to link such action space with foot placements as we move more from low-level to high-level reasoning. We really appreciate the funding agencies as well as the students for helpful discussion. Thank you for listening.